Alright, continuing our discussion of Riemann sums, I'm going to start taking limits of them and showing how we get the definite integral out of that. So let me explain what we're trying to do first of all. Let f of x be continuous on a closed interval. AB. Let me draw just a rough sketch. No real importance is needed in this picture right now. So I'll put A and B. For the purpose of discussion, it probably is easiest to think of the function as always being above the x-axis. We'll get into more details later on. But let's say it's just some sort of a wavy graph, generic nondescript graph, starting at A, ending at B. Whatever it does outside of A and B, I don't really care. Now what we're going to try to figure out is in between A and B, if I cordon that off with vertical lines, and then I start shading in underneath the graph, but above the x-axis. I would like to find the exact area under the curve. So the goal of everything here, let's put it our statement, our goal statement. The goal is to compute the area under the curve above the x-axis and between A and B. Well, the way we're going to do it is the following. I'm going to draw this picture several times. Just excuse me if it doesn't look exactly the same every time, but it doesn't need to be for what I'm about to do. Still want to start at A and end at B. Similar to what we did before, I would like to get the area under there, but I'm going to start by approximating it. So what we do is we lay down a partition that we'll call x1, x2, x3, and this will go on and on and on. xi minus 1, xi, dot, dot, dot. And by the time we get to B, that will equal xn. So A is supposed to be x0. For reference, A is x sub 0. And the markings between A and B go from x1 to xn. Now remember, in some way or another, we start drawing rectangles depending on where you make your selection, whether it's the midpoint, the right hand point, or something like that. It doesn't really matter where you do it, to be honest. Let me draw this. I'll explain to you in a minute what we're doing. I'm going to draw rectangles, but they're not necessarily the midpoint. They're not necessarily the highest or the lowest or anything like that. And you get the idea. Let me just kind of go over to xi to xi. xi minus 1 to xi. Now the way this particular subinterval looks like, it looks like x sub I minus 1 would be the lowest value, and then x sub I would be the highest value. So in the interval, the closed interval, x sub I minus 1, x sub I, let x sub I squiggle be the x value, of the absolute min on the closed interval from x sub I minus 1 to x sub I. Let x sub I star be the x value that produces the absolute maximum on that closed interval x sub I minus 1 to x sub I. So what do we know about this then? Let me draw a picture of just x sub I minus 1 to x sub I. On this interval, it could dip down, squiggle up, and all sorts of things. I really don't care. So in this picture that I'm drawing here, I'm going to locate for you where the x sub I squiggle is. So that would be the point that gets the lowest y value. So it is so illustrated. That is x sub I squiggle. And the one that gets the highest, I'll put a dot where the highest point on that curve is. That is x sub I star. So what do you have? No matter what, f of x sub I squiggle is less than or equal. I mean, this could be a constant function or constant in some places. F of x sub I star. So, you are for each interval or each subinterval, you're choosing places where you have the lowest and highest values. So let me draw a picture of the graph again. I may stretch it out some because I may need some room. It starts at A, ends at B. A equals x sub 0, B equals x sub n, and then in between I have x1, x2, dot, 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 xi minus 1, x sub I, dot, 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 dot. And so my graph comes in here, does a bunch of stuff, and then on that interval, I'll kind of mimic what I did up there. So like in the first interval from A to x1, if I look in that interval there, the very highest point appears to be somewhere in the middle, not exactly in the middle, but somewhere where the highest point on, I would have an x1 star. And then the lowest point actually appears to be x1 in that particular interval, so that would equal x1 squiggle. Well, I'm going to do the same thing for xi minus 1 to xi. If I go and locate the smallest point on there and the highest point on there, then underneath these, underneath the lowest point on the x-axis, I'll have x sub I squiggle, and then x sub I star. Okay, now what's going to happen is we are going to create rectangles of height f of x sub I squiggle. Let me go ahead and make a rectangle of that height that is constant throughout that subinterval. Okay, so I get like a low rectangle. I'm also going to construct another rectangle that will be constant on that interval, and that will be the one that is the height of the highest y value. So what you have on the closed interval x sub I minus 1 to x sub I, f of x sub I squiggle is the lowest y value. F of x sub I star is the highest y value. The area of the rectangle rectangles is given by f of x sub I squiggle times delta x sub I and f of x sub I star times delta x sub I, where delta x sub I equals x sub I minus x sub I minus 1. That's the width of that interval. So delta xi is the width of the interval x sub I minus 1 to x sub I. All right, so here's what we do. I start and lay down my partition as before. So I've got a equals x sub 0, then x1, x2, dot, 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 xi minus 1 to xi, dot, 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 dot. And the graph, of course, hovering over it. Now, if I repeat this process and always pick these low rectangles versus these high rectangles for every sub-interval that we're on. So let me draw another one in here. There's the lowest point. And then I have the highest point. And then et cetera, et cetera, et cetera. Remember, the lowest, underneath the lowest point was my x sub I squiggle. And above my highest point is my x sub I star. And hopefully you can see the area under the rectangle of big rectangles is definitely bigger than the rectangle of little rectangles. What I'm saying is it's always the case that f of xi squiggle is less than, maybe mostly less than, but probably less than or equal to f of xi star, no matter what. Thus, if you do that for the entire thing, you have an x0 to x1, x1 to x2, blah, 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 then the sum, well, before I get to the sum, I can most definitely, for each of these inequalities, I can multiply both sides by the positive number delta xi. So I have f of x sub I squiggle delta xi is less than or equal to f of xi star delta xi. That way, then, the sums from I equals 1 to n, f of xi star delta xi is greater than or equal to f of xi squiggle times delta xi. Summation. I equals 1 to n. Notice that these are Riemann sums. What I'm going to do, and use this throughout, this is a collection of rectangles and we will be keeping track of their area. I am going to call this thing on the left capital A sub n, but with a bar underneath of it. That's going to be the sum from I equals 1 to n, f of xi squiggle delta xi, and then A sub n with a bar over it, I'm going to let equal I equals 1 to n, f of x sub I star times delta x sub I. And I'm going to consider subtracting them. It's clear to me, it should be clear, it's clear that A sub n with a bar under it is less than or equal to A sub n with a bar over it. That's exactly what I just showed you up here with the sums. A sub n with the bar under it is on the left, A sub n with the bar over it is on the right up here. Okay, so consider A sub n bar above minus A sub n bar below. That's going to equal the summation I equals 1 to n f of x sub I star delta x sub I minus the sum I equals 1 to n f of xi squiggle times delta xi. And I'm going to bring these sums together by using the distributive property on the delta xi's. I'll get I equals 1 to n f of xi star minus f of x sub I squiggle times delta xi, since it was the same xi for each one of these things. Now, here's the gist of the proof. I can't go through all the details because some of the things I'm going to say and do require higher level math than what we have in here. Or, I mean, I could actually explain them, but it would take us so far out of the way, and there's some technical things I really don't want to get into right now. Basically, we do this. If you look at this, if n gets bigger and bigger, the rule is, as n gets bigger and bigger, the partitions become finer, finer, and finer. That means let's just take a look just the x-axis for a moment. If I go x0, and that's A, x1, x2, x3, x4, dot, 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 until I get to xn, which is equal to b. A finer partition would be that I add more slices in here than before. And notice I'm not necessarily making it true that the new slice pieces are in the middle or anything like that. And then what I'll do, after you have new slices in here to make a new partition, renumber them. So now my new x1, come on dude, my new x1 is closer to x0, my new x2 is closer to x1, x3, you get the idea, xi minus 1, xi. What's going to happen is we're going to require that as n gets bigger, you're going to add more division points in the partition. And we're also going to require that all of these subintervals, every last one of these things, all of them tend to 0 as n goes to infinity. So not only are we adding more division points along this, we're going to require that the distance between the beginning and ends of each and every one of them is going to 0. So here's what will happen in the scheme of things. At some point on the graph, let me expand my xi minus 1 to x sub I. Here's something that you notice on just that subinterval for a minute. If I look at the y value of the lowest versus the y value of the highest, x sub I squiggle, x sub I star. Let's take a look at their y values over off to the side. F of x sub I squiggle, f of x sub I star. If I squeeze x sub I minus 1 and x sub I so they're getting closer and closer and closer, x sub I squiggle, f of x sub I squiggle is going to be getting closer and closer to f of x sub I star. That's going to happen. Here's what we're ultimately going to do. We're going to say something like, let epsilon greater than 0 be given. Remember that thing? So I'm going to require that the distance between the f's be less than epsilon. Okay? So then what happens? Well, for an epsilon on this particular interval, there is a delta. On the x-axis, in which delta xi is less than that, there is delta greater than 0, such that if x sub I minus x sub I minus 1, or in fact, let me just keep reminding you what that thing is. That's the length of the ith interval, but it's delta xi equals x sub I minus x sub I minus 1. Okay. There is a delta such that if delta xi is less than delta, then f, I do not need absolute values at all because something's bigger than the other thing. I need f of x, I did an absolute almost. We have f of x sub I star minus f of x sub I squiggle is less than epsilon. And here's the kicker. I will put, I don't know what else to put here. I'll put some sort of a symbol so you know that this is where higher level math is required. There is a concept called uniform continuity that says I can find one value of delta such that delta xi is less than delta and f of xi star minus f of xi squiggle is less than epsilon for all of the i's. What in the world does that mean then? Well, I'm allowed, so the idea is this, for each x sub I x sub I minus 1 to x sub I, I can find its own delta for that particular interval, but I'm saying this concept called uniform continuity, I'll put it in quotes, will allow us to actually find one particular delta that will work for every single subinterval. That's a big one, and I can't stress that enough. But let's go back to where I had a n bar above minus a n bar below, and that was equal to the sum I equals 1 to n f of xi star minus f of xi squiggle times delta xi. Every single one of these f of xi's, f of xi star minus f of xi squiggle, if I require them all to be less than epsilon, I get this is less than the sum I equals 1 to n epsilon times delta xi. That is when this one delta will allow me to do this. Of course, I'm assuming, I should say before all this, assume delta xi is less than delta for all I. So then I can factor the epsilon out times the sum from 1 to n delta xi. Well, delta xi, that equals, and I'll write them, each delta xi I'll have x1 minus x0 plus x2 minus x1 plus x3 minus x2 plus dot dot dot, and then I get finally to xn minus 1 minus xn. What you'll notice is that the original, you'll notice is that the x1 cancels, and you'll notice too that the x2's cancel, and in fact everything's going to cancel in between. I messed up, this last one should be xn minus x sub n minus 1. Everything's going to cancel except for x sub 0 and x sub n. So this equals epsilon times x sub n minus x sub 0. Well, x sub n is b, and x sub 0 is a. So, what do I have? I have a n bar above minus a n bar below is less than epsilon over b, or times b minus a. And of course, that is greater than or equal to 0. What I could have done this whole time then is I could have specified epsilon to be something that is going to 0. I could have made the issue that epsilon equals 1, and then this quantity would be less than 1, or I could have said epsilon equals 1/2, and then this quantity would have been less than 1/2 times b minus a. Or I could have kept going. Say I made epsilon be some number that is shrinking. Say it's 1 over m. And this m gets bigger as the n's get bigger. Well, if that's true, then you would have something like this. 0 would be less than or equal to a sub n bar above minus a sub n bar below, which would be less than 1 over m times b minus a, and m is going to infinity as n is going to infinity. What will eventually happen as n goes to infinity, you would have I should have put the limit as n goes to infinity through all of these. So what I have then is that the limit as n goes to infinity, a n bar minus a n bar below, a n bar above minus a n bar below equals 0. Unfortunately, this does not mean that the limit of a sub n equals a sub n bar above equals the limit as a sub n bar below, because there's a second concept that we need. Concept number 2 involves a Cauchy sequence. And I will put that in quotes because that's something that we don't deal with. And it's no surprise to me that a Cauchy sequence is in there with uniform continuity, because a Cauchy sequence is sort of a sequence version of that. What we do is ultimately we do show that the limit of a n bar above equals the limit of a n bar below via a Cauchy sequence. And we end up showing that the limit that n goes to infinity, a sub n bar above equals the limit as n goes to infinity, a sub n bar below, through Cauchy sequences. So I'll stop there. When the limit does exist, and now you know that it does if you have a continuous function, when the common limit exists, we call it the definite integral. And write, here's that cool symbol again, the integral from a to b. That's the way it's said. You write the integral symbol, a in the bottom, b on the top, and we simply write f of x dx equals the limit as n goes to infinity, a n with a bar below, and that equals the limit as n goes to infinity, a n with the bar, I think I said bar below before, but bar above is the limit as a n goes to infinity, a n bar below. So all of that is necessary to prove that the limit will exist. And like I said, there's two big things. If you really want, I've specified them for you. If you want to go and look up Cauchy sequences and see what that stuff means, by all means have at it. You can even ask me, but it's not something that I want to go into in the class. And the other one was the uniform continuity that I had to invoke at some point. What these do is these do kind of it allows me to avoid all of the ugliness of the proof. Everything left is nothing but niceness and sugar and spice. But the stuff that I've avoided with these, and I've also avoided talking about how the an bar aboves will get smaller and smaller and smaller as n goes to infinity, and I didn't talk about how the bar below ones get bigger and bigger and bigger. So I will avoid doing so. And I think what we'll do next in the next video is then I will use this limit definition to redo those problems we were estimating, but I'm going to take the limits. Now in general, it doesn't matter what you pick. You can partition any way you like. That specifically was not mentioned, and the partition, what type of a partition, was not really mentioned. So you can use any kind of a partition you want, but rest assured that no matter what you do, let's say your partition or your area of rectangles is a sub y. No matter what, for any n that you can possibly have, your partition, the areas under the rectangles are going to be greater than or equal to a n with a bar below. And it's also going to be less than or equal to a n with a bar above. Now, since both of these a n's below or above both converge to the integral by the sandwich theorem, or squeeze theorem, whatever it was called in this course, the middle is also forced to converge to the integral a to b f of x dx. All three of these things will converge to the same thing because of the sandwich theorem ultimately will do that for us. And so the three methods we had left slash right slash mid point methods will all yield the same correct answer, because any one of those will fit between an lower bar and an upper bar. And so since an lower bar and an upper bar can converge to the same limit, whatever's in between is forced to converge well. That's why you can pick them in any way you want. There's no specification on how you pick them. Why do we have these three methods? Because they are absolutely the three methods that you can definitely get formulas for. You pick other methods at your own peril because you'll have some terrible looking formulas involved, if you can even get formulas for them. All three of this will allow us to use our summation formulas we developed a little while ago to get a formula that I can then allow n to go to infinity with. So this heavy section, and I've avoided the worst, heaviest stuff, but I had to avoid it. Don't think because I didn't include it I'm taking it easy on the course, because that material is definitely required for a higher level class. So you have the idea. I mean, you really do have the idea on how this works, since what they call the upper sums and the lower sums have the same limit because their limits are the same. It's like having a left and right limit. We say that the integral converges, and that's the way we'll check integrals to converge, is if the left and right, or the upper and the lower sums converge to the same thing.